So we're back to the classroom. So that's great. All right, so today I want to talk about some consequences of intersection theory, in specifically two very beautiful theorems. So let's start by talking about the winding number. So this is an instance where degree theory comes in, and it's very, very beautiful, and maybe you've seen this before. Or you've seen this in complex analysis in a different way, let me define it. So we suppose that X is a compact and oriented manifold without boundary. And let's say the dimension of X is n. Very often the manifold will be Sn. So often X is Sn. But sometimes it doesn't have to be. So let f be a function from X to Rn plus 1. And we pick a point that is in Rn plus 1 that's not in the image of f. So we'd like to define the winding number of this function with respect to this point z. Okay? So to do that, we define this auxiliary function u, which goes from x to Sn and takes x to f of x minus z over the norm of f of x minus z. Okay? And we define the winding number of f with respect to z to be the degree of this u. Okay, so this, you've probably seen this before in complex analysis. It's a very common thing. For example, if you have a curve and you take a point that's not on the curve and you orient the curve is the image of a map from S1 to R2. And you can talk about the winding number of the curve gamma with respect to this point z. And this is something you can also look at this in terms of computing some integral, some complex integral here, particularly for smooth curves in C. But the thing that's interesting is using degree theory can generalize this to higher dimensions. Okay? Yeah. So in this case, for this particular curve, you're really counting how many times you're going around this. And why is that? Basically, when you look at this function u, what it does is it takes your curve and you kind of first you take a transformation that takes z to 0, and then you divide by the norm. So then basically your u is going to be a map from S1 to S1 that basically goes like this, and then goes like this again, and then it goes back a little bit, and then it closes up. Okay? So this is going to be a map from S1 to S1 that's going to take 2 turns around S1. Okay, so then in this case, the winding number, so this is going to be the degree of this u, which is 2. Okay? So one way to see this here, in dimension 2, is you can take a line, half of a line that starts at z and goes all the way to infinity. And you see how many times this line intersects the curve. Okay? And here you have 2 times. But actually, it doesn't matter which line you take. Because if you take this other line here, here it intersects several times, 1, 2, 3, 4 times. But you have to look at the sign of the intersection. Okay, so then you have to count the intersections with signs, and it has to be the same thing. And why is it the same to intersect a line and to look at the degree? Because remember, the degree, by definition, is the intersection number of u with a regular value. So it's basically the number of pre-images of u, of this regular value by u. So this is the counted sign, the sign count of u inverse of A. So you look at all the pre-images of A by this map u, and you count them with signs. Okay? So what is a point here? So a point here would be a direction, and then you take the pre-image of that point by the map u. So that means you choose a direction, and you see all the points where the curve is going, where the curve hits that direction. Okay, so that's why this is enough. And of course, for generic line, this would be transverse, so that works. But it won't work if you, for example, pick a line that is tangent to the curve. That means that this direction, this vector here, is not a regular value for the map u. Okay, so this is kind of the first example of winding numbers. But the thing that's cool is that using this degree theory, we can define winding numbers in higher dimensions. Okay, I mean even in dimension 2 is already quite nice. Okay, any questions about this? Well, so here's an observation. So if you consider a homotopy of maps, or maybe I should say, we can call it a proposition. Let's go slowly. I think that, the course is going kind of fast. So proposition, so let's say that Ft is a homotopy of maps So these are maps that all miss Z. Okay, so these are maps whose image doesn't intersect Z, and the whole homotopy doesn't go through Z. So then, the winding number of F0, Z, usually my homotopy goes from 0 to 1. Then the winding number of F0 is equal to the winding number of F1, Z. Okay? So why is that? First of all, let's see the condition. You really need the whole homotopy to miss the point Z. It's not enough that the first map and then the last map miss Z. Okay, you can kind of really see this in dimension 2. So like in dimension 2, if I took this curve and I homotopy it around in a way that the curve never crosses Z, then I have the same winding number. But if I cross Z, even if like after the homotopy I still don't hit Z, they don't necessarily have the same winding number. Okay? I mean this is an easy proposition to prove, but let's prove it anyway. I guess it's instructive to see why. So how do you do that? So for F0 and for F1, we have maps U0 and U1. Say so. For F0, we construct the map U0, which is F0 of x minus Z over the norm of F0 of x minus Z, and the same thing for F1. F1 of x minus Z over the norm of F1 of x minus Z. And we know the winding number of these functions is by definition the degree of U0 and the degree of U1. But now, U1 and U0, they actually are homotopic. Because you can define a homotopy UT, which is defined to be, ft of x minus z over the norm of ft of x minus z. And here you see we have to use the fact that ft never hits z for this ut to be well defined. Okay, so that means that u0 is homotopic to u1. So we already proved last time that that implies that the degree of u0 is equal to the degree of u1. And then we're done, because this guy is the winding number of f0, z, and this guy is the winding number of f1, z. Okay? Here's another, interesting example. Well, I guess I can write here. If P from C to C is a polynomial of degree n, then the winding number of the polynomial on when you restrict it to the boundary on a very large circle is equal to n for some r very large. Okay? And the reason for that, is we showed last time that if you take a sufficiently big r, that the polynomial divided by its norm, the winding number with respect to 0, we showed last time that for a very large r, that p over norm of p is homotopic to z to the n on the boundary of a very large ball. In the map z to the n, over norm of z to the n, that map has degree n, as we also proved. Okay? So since this, then the winding number of p restricted to this ball over with respect to 0 is equal to the degree of the map z to the n over r to the n on this ball. And we show that this is equal to n. Okay? So that's an interesting example. Okay. So now I want to say what happens if you can extend your map to a disk. So let's say, for example, that you take this map that goes from the circle to R2 and say that you can extend the map to a smooth map on the disk. What can you say relating the winding number and this extension of the map to the disk? Okay, so here you can see that you can do that. Sometimes you can't do that. In this case, because the target is Rn plus 1, there are not a lot of obstructions to doing that. At least in a continuous fashion, it's not so hard to see you can do it because this guy is contractible and you can smoothen it out by a little perturbation. So it's kind of not hard to see that you have a map of the disk whose boundary is this curve here. So you can often do that. But now what I would like to say is, let me state the proposition, is basically that the winding number is going to be equal to the intersection of this map with the point Z. So the number of pre-images of Z by this map. So suppose that X is the boundary of D, and D is compact and oriented. And that F extends to a map, capital F, from D to Rn plus 1. So suppose you can extend this map to D. Then the winding number of f with respect to z is equal to the intersection number of f with z. Okay, so, most of you are online and, can't really interact with me right now, but what I'd like to ask you is, what's the problem with what I wrote down? There's a little catch. So you might want to answer if you've caught it or not. But anyway, the catch is that we didn't really define this intersection number for functions whose domain is a manifold with boundary. So no, this kind of makes sense, but we have to really say a little bit more about this. We haven't quite defined this. Okay? So this, what I mean by this is really like, the map F, if Z was a regular value, you looked at the pre-images of Z by the map F, and you counted them with signs. So this would mean this, a signed count. If Z is a regular value. But I'm not really assuming that. Anyway, so I think I should say a few words about what this means. It's pretty much, if you understood intersection theory so far, it's not hard to figure out what it means, but I think it's worth me saying a few words. So, basically, in this particular case at least, I think, we can say the following thing. So if X is compact, and Y has no boundary, so Y and W, so X is compact possibly with boundary. And Y and W have no boundary. And Y is closed inside of, W is closed inside of Y. And then what we really want is we want basically to have a function from X to Y such that the preimage of Y doesn't intersect the boundary of X. So if that's the case, first you assume that F is transverse to W. Okay, so if that's the case, then you can define the intersection. Then you can look at the preimage of W by F, and this will be a manifold without boundary, because it doesn't intersect the boundary of X, so it's transverse to X. It's transverse to W in X, and the boundary of F is also transverse to W because it doesn't intersect, because the image of W, the pre-image of W doesn't intersect the boundary of X. So that means that this is a manifold without boundary. Without boundary that's contained in the interior of X. So if we have the right dimension count, so if the dimension of X plus the dimension of W is equal to the dimension of Y, then this guy is a compact manifold of dimension 0 that's contained in the interior of X. So this is a compact manifold of dimension 0 contained in the interior, the interior of X. And moreover, if everything is oriented, if X, Y, and W are oriented, then this will also be oriented. So, if everything is oriented, if X, Y, and W are oriented, then this guy will be oriented too, with the usual orientation that I explained last time, or maybe 2 classes ago. So that means that you can count these points with signs and say that that's the intersection number. Okay? So I guess we could have already said that last time. But the thing that is a little tricky, so we can define the intersection number of f and w in the transverse case, at least, to be basically the sum of the signs of the points in the intersection. Okay? But the thing that's a little subtle here is that, first of all, if you want to homotope the function, you can't homotope the way you want. You have to homotope in a way as to preserve this condition. Okay, so if ft is a homotopy such that basically the preimage of w never intersects the boundary of x, then you're good. Then the intersection number of f0w is equal to the intersection number of f1w. But basically, if you start homotoping maps that have where the domain has boundary, this condition could be violated. And so that these points could be shooting up to the boundary and disappearing. So that's why this count wouldn't be constant in general. Okay? But if you don't allow the function to ever to ever have the image intersecting w, then this is okay. Okay, so in particular, if you pick, if f is a function that's not necessarily transverse, but f satisfies the property that its image doesn't intersect w. I mean, that's the same thing as that the image of the boundary doesn't intersect w, which is the same as this that equation. Then we can perturb f and find something that's and find because these two are because the complement of w is open, then we can find a g such that basically f is homotopic to g by maps not intersecting w. And then we can use g to define the intersection number. So then define the intersection number of f and w to be the intersection number of g and w. Okay? I mean, it's the easiest to think about the case where w has dimension 0. And the two, and x and y have the same dimension. So the case of the degree. So what you really want is you can have a map from a manifold with boundary to a y, something else, and you can take the pre-image of a bunch of points and count them, and that is invariant as long as the points don't shoot off to the boundary of x. So that invariant by homotopy. So that's kind of the subtle thing. But anyway, any questions about that for people who are here? Yeah, that's what I forgot to write down. Find g such that g is transverse to w. Yeah. Okay, so it's kind of exactly the same thing as before, but you have to be careful with this condition that you need the whole homotopy to not cross the boundary of, you need it, through the whole homotopy, the boundary never gets mapped to a point in W, because that's where things can fail. Okay? All right, so I think now the proposition maybe, is completely clear what it means. And it doesn't require, the map to be transverse to Z. Although, you know that if it's not transverse to Z, then you can perturb it a little bit so that it will be transverse to Z. But even still, this makes sense, even when it's not transverse to begin with. Okay, so let's prove the proposition. Actually, before I prove the proposition, let's go back to that picture that we had, and let's kind of interpret the proposition in light of that picture. So, in dimension 2, we had this picture where here was my point Z, and then I think I had some curve that looked kind of like this. Okay. So if this is my curve, this is my map F from S1 to R2. And now I can think about extending the map F to a map of the disk. And the point was F did not touch the point Z, but the extension of the map to the disk will. As long as the degree, the winding number is different from 0, then this number has to be different from 0, which means that F has to hit this point at least. And it's not hard to see actually that you can, one way that you can do that is by just like contracting the loop to a point, and that will give you an extension of the map from S1 to D2. Or you can think about a disk that comes here, goes like this, like this, and also has a part here. I mean, it's just a map. Of course, it's not an embedding or anything, or you can actually find an immersion, but not an injective immersion. And it's not very hard to see in this picture that the map that I chose here for this point Z will have two pre-images. Okay, so I guess from this picture, it's not very hard to believe this proposition. Okay. But anyway, we're not here to believe propositions. We're going to prove them. So let's prove the proposition. Okay, so we could perturb F to be transverse to Z, and again we can perturb. Yeah, so since basically the image of F doesn't intersect Z, that means in particular F is transverse to Z. And using one of those corollaries that from Thom's transversality theorem, that means if we can extend it to a map F, then we can perturb it to make sure that it's still transverse to Z. So we may assume, without lots of generality, that F is transverse to Z. In other words, that Z is a regular value of F. Okay? So okay. So now I have to consider the case when the pre-image is just the empty set. So I guess the first case to consider is if capital F inverse of Z is the empty set, then what happens is you can take that map U and you can actually extend it to the whole disk. That means that then the map U, which goes from x to Rn minus Rn plus 1, can be extended to a map that I could call a capital U that goes from D to Rn plus 1, which basically has the same definition but for capital F. So U of x equals f of x minus z over the norm of f of x minus z. And remember, there was a lemma that we proved that if we had a map that could be extended to a compact manifold with boundary the original thing, then the degree was going to be 0. Okay? So that means that the degree of u, the degree of little u, which is the winding number of f with respect to z, is 0. Okay? And of course, the preimage of z is 0, so that's also the intersection number of f and z. Okay, there are no points in the preimage. Okay. All right, so now let's suppose it's not. So now suppose that the preimage of z is a bunch of points x1 through xn. Okay. So now we're going to do something that's going to look a lot like complex analysis, but it's actually in higher dimensions. So by the inverse function theorem, because we're assuming that z is a regular value, near each one of the preimages, maybe x1 through xk, at each one of at all of the xi's, we have a local diffeomorphism. So by the inverse function theorem, f restricted to xi, no, I'm going to write it like this. F is a local diffeomorphism near each xi. So that means, that you can find neighborhoods of xi that are all disjoint So we can find disjoint neighborhoods ui of xi and v of y such that f restricted to ui takes ui into vi, and these are diffeomorphisms. And you can choose the same v because you can just take the intersection of all of them because it's a finite number. Okay? And moreover, because this is a diffeomorphism, that means we can take charts to Rn so that it's the identity. So we can choose charts on potentially smaller open sets, but I'm kind of just making sure ui is small enough to be in the domain of a chart. And psi from V to Rn such that psi composed with f composed with phi I inverse is the identity. I mean, this is just literally once you know it's a diffeomorphism, then you're going to end up with a diffeomorphism of Rn. So you can compose one of them by the inverse of that diffeomorphism, and you get the identity. The only thing is that now these maps might not be orientation preserving. So you look at these maps phi and psi, and you have a chosen orientation. When you have a chosen orientation, you basically now this phi I and this psi they don't have to match the orientation. So what you actually want to do is you don't want to choose arbitrary psi and phi, but you want to choose psi and phi so that basically so that psi and phi preserve the orientation. So that would mean that the composition will either be the identity, which is the case when f preserves the orientation. So the derivative of f is a map, is an isomorphism that preserves the orientations that are given. Or, if the reverse is the orientation, then you want to choose another, something else that's kind of represents the orientation reversing thing. So it's kind of the simplest thing you can find. So basically, we're going to choose orientation preserving charts. Such that it's either this or psi composed with f composed with phi inverse is the reflection. I don't know, on the first coordinate, for example. So this is a reflection. R is a reflection. I mean, could be any of them. For example, R of x1, x2, xn is minus x1, x2, xn. Oh, sorry, this is n plus 1. I mean, doesn't matter. Okay. Okay, so I hope that's clear. Let me just say one more time why this is true. So you can always choose charts so that you get the identity, basically, if you don't require them to be orientation preserving. So if you want them to be orientation preserving, basically the whole thing, the orientation preserving is something that pairs up. So if you have, if you know that f is orientation preserving, and you happen to have two things that are orientation reversing, then you can apply a diffeomorphism that's orientation reversing and make them, two of them on both sides, and make the whole thing orientation preserving and still have the identity. And if the f is orientation reversing, then it's kind of the same thing. So, but then you actually have to choose. If the whole thing was the identity, then it's in some place you have to be switching the orientation. You can't get rid of that. So, you can always find a diffeomorphism, a linear transformation that will take it, orientation preserving linear transformation that will take it to the reflection. Okay, so that's because if you look at the equivalence classes of linear transformations, they are determined by, if they're invertible, then they're either sort of equivalent to the identity or to a reflection using the positive determinant matrix. Okay. So anyway, that's some basic linear algebra. But maybe it's a little obscure if you haven't seen this. And I already said this. Basically, I already used this last time, but I'm using it once again. And I hope that if you didn't understand it last time, you understand it now. Okay. So now I'm going to choose little balls that are contained in these UIs. So now let epsilon be so small such that the ball, so that there is a ball of radius epsilon contained in phi I of ui for every I. Okay. And here, it doesn't matter if you choose 0 to be there and you take the ball centered at 0, or you just take a ball centered at some other point. You might as well assume that the image of your xi is 0, and you take the ball centered at 0. But you see, it doesn't really matter. But maybe we can assume that that phi I of xi 0. And maybe psi of y is 0. Okay. So now we can define, maybe I'll call this Z, this set D minus the inverse image of these balls. No, n plus 1. The union over I. Okay, so basically here's my D, and I have this map F that goes to Rn plus 1, and I take a point Z, and I look at the pre-images, and I look at little balls around them. Okay, so now what we know is that the Z does not belong to F of capital Z, right? Because I basically isolated all the pre-images of Z in these little balls, and I removed these balls. So then Z is not in here. So that means that if I look at the map U on the boundary of Z, the intersection number of that has to be 0. So the degree of this map, so that means that the degree of the map U restricted to the boundary of Z has to be 0. Okay, remember what the map U was. The map U was simply, U of x was f of x minus, I guess in this case, it's capital F of x minus z divided by capital F of x minus z. And it really, of course, is only defined when f of x is not z. Okay? But anyway, I still have something of dimension n, and this takes values in Sn. So when defined, this takes values in Sn. Okay? So this, this thing makes sense. And this is because this map U restricted to Z can be extended to a map on all of capital Z. Okay, so this is the intersection number of U restricted to the boundary of Z with the point little z. Okay, so this is capital Z, and this is little z. Okay, so what the nice thing now is that what is the boundary of Z? So the boundary of Z is the boundary of D union with the boundary of these balls, but actually they come with a negative sign. With respect to the usual orientation. So when you orient these balls usually in the usual way, but when you see the sphere as the boundary of what's outside, then that has the opposite orientation than when you see the sphere usually with the way that you do, which is you orient it with the orientation induced by the ball. So that means we can kind of write this Z union minus phi inverse of the boundary of the ball. Okay? So that means, that this, from this equation here, let me put this in a box. So that means that this intersection number here is going to be sort of the intersection number of U with the boundary of D minus the sum of the intersection number of U over here. So restricted to phi inverse of the boundary of the ball, Z. Okay. All right, because I'm changing the orientation of all these guys, so I get the same intersection number as this, but with the opposite sign. Okay, so now, now we kind of want to compute this guy. So what this equation is saying is that, basically the winding number of, so U restricted to D, to partial D, is F, is what we called little f. So the winding number of F with respect to Z is equal to the sum of the winding number of what you could call Fi restricted to Z. Where, Fi is just this other map, where Fi is just capital F restricted to this boundary of the ball. Okay? So, the idea is I had this function f here. I extended to this, capital F everywhere. And when I take, so this is kind of my f. So now I have these little f's, f1, f2, f3, etc. And the nice thing is, I exchange the winding number of f, some function on some kind of big thing, to a sum of winding numbers of functions that, extend to local diffeomorphisms. So now I can do the calculation by hand in these little neighborhoods, in these little balls. Okay, so now it remains to compute the winding number of these Fi's, but that's actually kind of a straightforward calculation. So now we need to compute these winding numbers. Now we need to compute the winding number of Fi with respect to Z. Okay. Well, so what is that? Remember that we have basically two kinds of xi. So we have the ones where f is is positively oriented, and the ones where f is negatively oriented. And because these guys preserve orientation, these charts preserve orientation, the winding number of f is going to be the same as what happens after you look as a map from Rn plus 1 to Rn plus 1. So you can look to it in charts. So since phi and psi are orientation preserving, we can look at basically the winding number of Fi with respect to Z is going to be the same as the winding number of psi composed with Fi composed with phi inverse with respect to 0. Kind of just map it to map from Rn plus 1 to Rn plus 1. And then this you can compute by hand. Basically if you take the identity map with respect to 0, that obviously has a winding number of plus 1. So this is going to be exactly sigma I, where sigma I is 1 if, I guess I can just say, no, let's just leave it sigma I. So where sigma of I is 1 if this map here inside is the identity. And it's not a hard calculation. It's kind of a simple calculation. You just have to look at the orientation to see that sigma I is minus 1 if this map is the reflection, or is any reflection, actually. Okay? Okay, so now we're almost done. The last thing we have to notice is basically, this is the same as the sign of this sigma I is the same as the sign of this pre-image. So the pre-image, of course, the pre-image of y by Fi is also just xi. Because, capital F was a local diffeomorphism here. This is not Fi, it's capital F. in the preimage of this ball. But what we have to observe is that the sign of this xi is exactly this sigma I. So if f is orientation preserving, then the sign of this xi is going to be plus 1. And if this f is orientation reversing, then the sign of xi is going to be minus 1. So basically the sign of xi as, a point in the preimage of y is going to be equal to this sigma I. Okay? So that means that the sum of these winding numbers is going to be the sum of these sigma i's. So it's just the sum of these signs. So that means that the sum of the winding numbers of these fi's with respect to z, this is the sum of the sigma I, which is equal to the intersection number of f, capital F, with z. Okay? So now putting this equation here together with this equation here, we are done. Okay, so the winding number of f with respect to z is the intersection number of capital F with respect to z. So the number of preimages of capital F. Okay? So that's the proposition. Okay, any questions about this? No, okay. So now we're going to prove some beautiful theorems. Okay, so let's start with the Borsuk-Ulum theorem. Well, the Borsuk-Ulum theorem is a very classical theorem, and it says the following thing. So take a function from Sn to Rn, any smooth function. Actually, the theorem is true for continuous functions too, but we don't have, the tools would require some approximation. So, we're just going to prove it for smooth functions. It's good enough for most physical applications. Then there exists two antipodal points that have the same value of f. So there exists a point in Sn such that, I can write it here, such that f of x is equal to f of minus x. Okay? So you can think of, for example, if you look at the Earth, which is an S2, and you take two parameters like temperature and pressure. So then there exists 2 points that are antipodes on the Earth that have exactly the same temperature and the same pressure. So every time there are always 2 antipodal points on the Earth that have that. Or if you take the equator, for example, there are always 2 antipodal points on the equator that have the same temperature, because that's a circle. But then you can only get one thing to be the same. Getting 2 things would not. That's not true. Okay, so what's the proof of that? Okay, so once you have a function like that, then the whole point is to build an odd function that doesn't vanish. So, suppose not. So if that's not true, then we can we can define a function g of x to be f of x minus f of x is an odd function that never vanishes. That doesn't vanish. Okay, that's never 0. And we're going to get a contradiction here. Okay? So to get the contradiction, we basically, we need to look at the degree of something. So to look at the degree of something, you could try to, basically take this guy, the function that never vanishes, and divide by the norm. But then you would find a function from Sn to Sn minus 1. So, it's a little hard to, you can't quite talk about degrees there. You can, you could do it that way and use some homology or something. But because we only have degrees, you have to be, a little trickier. And first, we actually are going to extend this g to a function that takes values in Rn plus 1. So, to prove that this is not possible, we're going to define another function that I'll call g prime that goes from Sn to Rn plus 1. And we're going to talk about winding number with respect to the origin, or the degree of this divided by its norm. So this is just going to be the function that g tilde of x is going to be g of x 0. So basically I'm just kind of putting this map g. So g, g is a function from Sn to Rn. But I'm just going to put this into one more dimension. Just this embedding the Rn into Rn plus 1 in the normal way, as the 0 hyperplane. Okay. So, this is in Rn, and this is the 0 in R. Okay. So then, of course, this g tilde is still an odd function. Then this g tilde is odd. And 0 is not in the image of g tilde. Okay. So the claim is that if the function is odd, then its winding number with respect to 0 will be odd. So in other words, if the winding number is just the degree of this map when you divide by the norm. So you're going to have an odd map from Sn to Sn, and I claim that that odd map has an odd degree. Maybe that's why it's called an odd map. But so the claim is that g tilde has an odd winding number. The tilde, or the winding number of g tilde with respect to 0 is odd. Okay? And we'll show the claim in a little bit. But let's suppose the claim, and let's see how we get a contradiction with this fact. With g of Sn. You need this to be able to define. But let's see how we get a contradiction here. So basically, that will be a contradiction if you think about it in a way, because the image of g is kind of contained in Rn. So it's really small. So if you think about your g tilde, it's taking your Sn to Rn plus 1, but really the image is contained in just one thing. So if when you divide g tilde by its norm, then the image of that will be contained in the equator of a sphere. So that's why it can't have an odd degree, because the degree it's something that it's contractible on the sphere, or in other words, it doesn't hit most points of the sphere. Okay, so that's why that's going to be a contradiction. So let me just write this down. So assuming the claim, the winding number of g tilde with respect to 0, this is the degree of g tilde over the norm of g tilde, is odd. But, so if you take, for example, 0, 0, 0, 1, 0, 0, 0, 0, 1, this is not in the image of G tilde over the norm of G tilde of Sn. So it's kind of an obvious contradiction, because it's very easy to find points that are not on the image of the map. Because the image of this map is contained in Rn times 0. So if you take something that's not non-zero here, then it cannot be in the image of this guy. Right? So that means it's a regular value in particular. And the intersection number with this point is 0. So that means that the degree of this map is the number of preimages of any regular value. For example, a regular value that's not in the image. So this is 0. And that's a contradiction with it being odd. Okay, so that's not possible. So now we have to prove the claim. So now I guess you could say that the Borsuk-Ulum theorem is basically this claim. Okay, the claim that if you take an odd function from Sn to Rn, then or an odd function from Sn to Rn plus 1 that misses 0, then the winding number with respect to 0 is odd. So some people just say that's Borsuk-Ulum's theorem, like it's equivalent to the original theorem. But the original theorem is kind of prettier, and it's more, it's easier to see applications for it, or to at least remember the statement. And it was the original formulation. Okay, so what we're going to prove is that this winding number of G tilde is odd. And we're going to do that by induction. So proof of the claim. So we're going to apply induction. Okay, so first of all, the case n equals 1. Okay, so now I have a map. So I'm going to start calling this map G tilde something else, like let's say, well, let's just keep G tilde. I don't want to confuse you. So G tilde is a map from S1 to R2 minus 0. It doesn't hit 0. And G tilde is odd. So now we can take, of course, the map G tilde over the norm of G tilde. And that's going to make a map from S1 to S1, which is odd. Okay? So now, when you have a map from S1 to S1, then you can lift this map to a map of R to R. And that's kind of a, I guess you can think about this as like a covering spaces argument. But in this particular case, you can do it by hand. So then H can be lifted to a map H bar from R to R. With the property that H bar of t plus 2 pi is equal to H bar of t plus 2 pi k for some k integer. Okay? So every map from S1 to S1 can be lifted to a map like this, where you just kind of you just choose one. You can think of S1 as being R over 2 pi z, and you just take the image of one of, the interval between 0 and 2 pi, and that will give you the beginning of H bar, and then you just kind of glue it together. So this will be taken to some interval of R, But basically, because when you get to 2 pi, you have to have the same thing as the image of 0 modulo 2 pi z. Then you have this 2 pi k. OK. So now, so this is just because it's a map from the circle to the circle. But now, since h is odd, then we actually have the property that when you add pi, h of t plus pi, you actually have to get h bar of t plus pi times k. So it's even where k is an odd number. Okay, so it's even more restrictive because when you flip t, you're supposed to get minus t for, because h of minus t is minus h of t. So you have this property here. But it's actually the same k because if you suppose this one, then this implies this one for the same k. So this k here is actually the same as this k here. And then now, basically this k is the degree. So, now it's not very hard to see that this k is the degree. So the degree, moreover, I guess I should say that. The degree of h is actually this k. Okay? So, we concluded that k was odd from this equation here. So this is the degree of h, which is, of course, the winding number of g tilde with respect to 0. Okay, so that's the starting case of the induction. Okay, so now let's suppose, that every odd map from Sn minus 1 to Rn minus 0 has odd degree, or has odd winding number. Winding number with respect to 0. Okay, so that's the induction hypothesis. And let's show that that's true for n. Okay. So now I'm gonna now start using f and g again, or actually just g. So let g be a function from Sn to Rn plus 1 minus 0, which is odd. So now I want to prove that this guy also has an odd winding number with respect to 0. Okay, so let Sn minus 1 inside of Sn be the equator. So the intersection of Sn with your usual the first n minus 1 coordinates, and let h be. So now I'm redefining these letters. G with restricted to the equator. Okay, so now fix a regular value. So let a in Rn plus 1, in Sn, be a regular value of both g and h, or g over norm of g and h over norm of h. Okay, so this guy has a bigger domain than this guy. Or the domain here is all of Sn, and the domain here is Sn minus 1. But the target of both is Sn. So this guy goes from Sn minus 1, goes from Sn to Sn, and this guy here goes from Sn minus 1 to Sn. Okay, and I can always choose a regular value of both of them because I know the set of critical values of any function has measure 0, so the critical values of two functions has measure 0, so I can always find a regular value of a finite number of functions that I choose if they have the same target. Okay. So, it's easy to see that minus a is also a regular value for both of them. Is also a regular value of both of them. And the other thing is, and moreover, so hence, G and H intersect the line L, the line generated by A transversely. Okay, this is a simple exercise, and I kind of drew a picture of this earlier today. That if you intersect, when you divide by the norm, you intersect a certain value of on the sphere transversely, or meaning a regular value. Then when you remove the condition of being divided by the norm, and you consider the whole line spanned by that intersection is transverse. Okay, so that's a very simple little, if you want, I can say this is an exercise, but if you don't understand this, then it's an exercise. But maybe for some of you, this is straightforward. Okay. And then, because this is a transverse intersection, just by account of dimensions, it means that the H does not intersect this line. Okay. Or, it's the same thing as saying that A is actually not in the image of H over norm of H. Okay, so moreover, H of Sn minus 1 does not intersect L. Or equivalently, neither A nor minus A is in the image of H over norm of H. Okay? And here I'm using the fact, to say that if you choose a regular value of this, then minus a is a regular value of this, then I'm using the fact that the function g and the function h are odd. Okay? So now, we can compute the winding number of g with respect to 0, and that's going to be the degree, of g over norm of g. And because A is a regular value of g over norm of g, I can just look at the number of preimages of g over norm of g. Okay? So this is going to be the number of preimages of A. And this is a signed count. Okay, so I'm putting the number here, but I really mean, as usual, the sum of the signs of all the points. Sorry, this is g over norm of g. So the number of points in the preimage by this guy of A. And then now I'm going to use the fact that g is odd again. So basically, if the number of times, the number of preimages of A is going to be twice as many as the number of preimages of g over norm of g of A n minus A. So this is going to be basically 1/2 of the number of the intersection of G with L. So that's the fact. Okay, basically because intersecting G over norm of G, basically it intersects A exactly the same number of times that G intersects the positive part of this line. Okay, so I kind of drew the picture in one dimension last time, but sort of if you think about your sphere like this, and here's your 0, and you take a line in a certain direction, the line will intersect the surface. There's a bijection between that and the number of times that when you divide by the norm, then you have A, which is the unit vector here, is going to be a regular value of this, and the preimage of A is going to be at some point on the sphere. So, clearly, every time you have this intersection here, you're going to have a regular a preimage of this guy here, and vice versa, and they are going to have the same sign. Okay, there's something to check, which is kind of part of this exercise here. But basically, you add one dimension, and it's this radial direction. And kind of the radial direction, kind of because of how we defined the orientation on the boundary, with the outward normal coming first, those signs are going to coincide. So that's why we kind of have this equality here, even with signs. Okay, but actually it doesn't matter because we're just trying to prove it's odd. So to something is odd, it could even be mod 2. So actually the sign doesn't really matter. But anyway, it's actually true with signs. And then now, this is basically the intersection number of some function that I'll define in a bit, g plus with the curve L, where g plus is the restriction of g to the upper hemisphere, to D, where D is the upper hemisphere. Say x n plus 1 bigger than or equal to 0. Okay? So this part here is D. And and here's my Sn minus 1. And why is that? Because I have a line that doesn't intersect the equator. So every time it intersects the image of G intersects this, it's going to intersect 2 points, one in D and one that's not in D. So that's why we get this equality here. Okay? And then we're almost done. And see, this thing is well defined, because L doesn't intersect the boundary of G plus. Now we can let PR denote the projection that goes from n plus 1 to the orthogonal complement of L, which is isomorphic to Rn. So let this denote the orthogonal projection. And note that 0 is a regular value of the projection composed with G plus. And that's because L is transverse to G plus. I guess it's equivalent to L being transverse to G plus. It's the kind of argument we've done so many times. Like being transverse to something. Actually, we usually write it the other way around. The function is transverse to the submanifold. So the function is transverse to the submanifold. It means that when you take the projection to a complement, in particular the orthogonal complement, that 0 is going to be a regular value. And kind of when you look at the preimage of 0, that is equal to the preimage of L by this G plus. Okay? And moreover, this guy is an odd function when you restrict to the boundary of D. This is an odd function. It doesn't hit 0, so this is an odd function. Okay? So basically, here we have it. It doesn't hit 0 on the boundary because L doesn't intersect the boundary of this D. So then, therefore, we have that the winding number of G with respect to 0 is equal to this I of G plus of L. And that's going to be equal to the number of preimages of this guy. So basically, this is going to be the winding number. Or let me write it like this. So this is I of PR composed with G, the number of preimages of 0. And by the proposition that we proved earlier, no, sorry. This is what's true. So in the whole disk, G plus, because of this equality here, and the equality comes with the orientation. So the number of preimages here is the same as the number of preimages here. So this is what we had from the proposition. No, sorry. This is what we have from this equality. And from the proposition, we have that this is the winding number of this function restricted to the boundary of D with respect to 0. There you go. So this is by the proposition. Okay? And by the induction hypothesis, this is odd. So this is odd by the induction hypothesis. And then we're done. Okay? So we proved the Borsuk-Ulum theorem. So we proved it by the induction. All right. Any questions? So let me just say one more time. How did we prove it? We had this function from Sn to Rn, and we suppose that there are no antipodal points where the function is the same. So then when you take the difference between f of x and f of minus x, you get an odd function. And that's how you kind of start the thing. So you have an odd function from Sn to Rn that never hits 0. So then you kind of cook up a contradiction. Okay? All right. And in particular, you prove that every odd function from Sn to Sn has an odd degree. Okay, and somehow it's a little easier for the proof to use these winding numbers. I mean, you could do it directly and just kind of prove that an odd map from Sn to Sn has odd degree, and basically if this map comes from a map from Sn to Sn minus 1, then that's a contradiction. You can kind of go like that, but yeah. But anyway, I think it is easier to use the winding number stuff and to kind of go through Rn. As you see, it's not very hard. But anyway, there are other proofs. There are many proofs of this using algebraic topology and using other methods. Okay. Any questions before the next cool theorem? All right, so the next theorem is the Jordan-Brouwer separation theorem. So, some people call it, some people know the Jordan curve theorem. So the Jordan-Brouwer separation theorem. Okay, so, people know, well, let me state the theorem. So let X be a compact, connected hypersurface so you just need it to be compact and connected. You don't need to be orientable at first. Then the complement of X has exactly two connected components. So it's the disjoint union of U1 and U2, where U1 and U2 are open and connected. And U1 union X is a compact manifold with boundary X, and U2 is unbounded. I guess maybe you should say U2 union X is a manifold with boundary. And U2 is unbounded. I mean, of course, that only really makes sense because we are in Rn. So it makes sense to say that a set is unbounded. But it's kind of obvious that it is once we have this decomposition, because X is compact, and U1 union X is compact. So U2 is going to be the complement of that. So it has to be unbounded. Okay, so that, I guess, is parentheses. Okay, so let's prove this. So for this proof, we're actually going to use winding numbers mod 2. So the whole intersection, I kind of mentioned that last time. But the whole intersection theory that we did, I kind of did directly the oriented case. So that I didn't have to say the same thing twice. But on the flip side, I didn't really talk about the mod 2 intersection theory. But once you know the oriented intersection theory, then it's the same thing, except that you don't require orientation. And then when you're counting points, they don't have signs. So you just literally count them, how many points you have, and everything is mod 2. And I mentioned this last time. When you have a homotopy, then when we show that the homotopy, the index number, the intersection number was preserved by the homotopy, we kind of said, okay, we're going to have these compact one manifolds. And the boundary of compact one manifold is going to be the union of points, and you have the same number of points to the plus and the same number of points to the minus. But from a non-oriented perspective, these things don't come with an orientation, but the boundary of a compact one manifold has an even number of points. So that's 0 mod 2. Okay, so so basically, you have to set up the mod 2 intersection theory. But it's kind of exactly the same thing. So I'm not really going to do it, but I'm just going to say sort of if X, it's kind of what I did before. If X, so let's say if X, Y, and W are manifolds, and X is compact. I kind of wrote this down earlier today, and Y is closed inside of W is closed inside of Y, and W and Y have no boundary. And then you have a function which is such that f of the boundary of X doesn't intersect W. Then, and I guess you start with the case where it's transverse, but as I explained, we can just define the number of points here to be, well, let me say, let's suppose that this is transverse. Then we define this guy, mod 2, to be the number of points of the preimage, mod 2. So it's 0 or 1. So it's 0 if it's even and 1 if it's odd. And then you can prove everything. Like you can prove that if you have a homotopy satisfying this condition, then this number is preserved if the last guy is also transverse. And then you can also prove that if it's not transverse, then you can perturb a little bit to achieve transversality, and you can define this even for non-transverse things. And then if now f, oh, sorry, no, to define this, we also need the dimension. So we also need the dimension condition. Okay? So now in the case when the dimension of x is equal to the dimension of y, and y is connected, we can talk about the degree of a function. So and now if the function goes from x to y, then you can talk about the mod 2 degree of the function. And that's just the intersection with a point. Or in other words, the number of pre-images of a regular value. So where f intersects a transversely. Okay? And from the degree, we can construct a winding number. So from the degree, we can construct, so if now f is a function from x dimension n into R n plus 1, and x has no boundary and compact, then we define that function u that goes from x to Sn, and we take a point z, which is not in the image of x. Then we have this map, u, maybe I'm going to call it uz now, and uz is x, f of x minus z over the norm of f of x minus z. And we can define the winding number of mod 2 of f with respect to z to be the degree mod 2 of this function uz. Okay, so it's exactly the same thing as before, but you just don't worry about signs. And you just add everything, and you look at everything mod, everything mod 2. Okay, so that's the degree 2, the mod 2 intersection theory. And just using that, we can prove the Jordan-Browse separation theorem. So let's prove the theorem. So proof of the theorem. Okay, so the idea is that we can use the Jordan-Browse separation theorem to divide the complement of x into, the idea is we can use the winding number to divide the complement of x in these u1 and u2. Okay? So I guess the step one is to show that Rn, I know that Rn minus x is going to be an open set because x is closed, x is compact. But I'm going to show first that this has at most 2 connected components. Okay, so first I'm going to show that it has at most 2. Then I'll show that it's exactly 2. And they can be distinguished by something that has to do with winding numbers, mod 2. Okay, so let's show that it has at least 2, at most 2 connected components. So for that, I fix some x in x. And let's say u is an open connected set. Okay. Hold on. Yeah. So, and let me draw a picture. So in a chart, basically, if I have a hypersurface x, and I take a point x, little x, on the hypersurface, and here's my u. So I can think about u as a little ball in Rn, and x there is going to be sort of the xn equals 0 plane. So sort of in a chart, I have that my u is this, my u is a ball, and then this is my x, and my point x is the 0. Okay, this picture is going to be important later. Okay, so now I take a point z that's not. So now I take a little z that's in Rn minus x. So z is somewhere here. Okay, so what do I do now? So basically now I can find a curve that connects x, and z because Rn is connected. So let gamma be a curve connecting x and z. It's a curve in Rn, and by transversality, I can assume that gamma is transverse to x. Without loss of generality, we can assume the gamma is transverse to x, but it's a curve with a compact domain. So it will have to intersect x at a finite number of points. So the intersection of gamma with x will be the point x, and then the points p1 through pk. So here I think of my curve as I'm going from 0, 1 to Rn. And I have these points, and I'm ordering these pk's with respect to the time that they attained. So that means gamma of pk of sort of tk. So that means I have points 0, t1, tk, 1, and I want gamma of pi to be ti. Okay, so you can think of this curve as kind of going like this. Boom. And then I have P1, P2, P3, P4, P5 or something. And I want to look at the last one. So I want to look at PK. So basically because of this property, after PK, my curve doesn't intersect x anymore. So if that means that if I take the curve gamma restricted to PK plus epsilon, 1, this curve doesn't intersect x. Okay, so let me expand my picture here so you see what's happening. So here's x, here's z, and then my curve maybe intersects x a few times. And then this is my tk, my pk. Sorry, not pk, tk. So after tk, I don't intersect x anymore. Okay. So now I have to use the fact that the manifold x is connected. So since x is connected, I can find another curve that connects p to x inside of x. Okay? So we can find a curve gamma tilde inside of x connecting x and pk. And now by the tubular neighborhood theorem, so if this is my x, I can use the tubular neighborhood theorem to say that a neighborhood of this path, so a neighborhood of this path is diffeomorphic to sort of a little ball is diffeomorphic to a little ball in dimension n minus 1, which is the part in x, times like an open interval, minus 1, 1. Okay, maybe you can think of this like box thing, or maybe a cylinder. Okay? So now what I want to see is I want to look at, gamma of tk plus epsilon. Yeah, tk plus epsilon. So, pk is gamma of tk. So when I look at gamma of tk plus epsilon, this is no longer an x, but it's in this neighborhood. So this is my gamma of tk plus epsilon. Okay? So it's going to be either on this side or on this side. So basically, this coordinate is going to be either negative or positive. Okay? And because of this tubular neighborhood theorem, I can connect this guy to the equivalent side near x, or to the positive side near x. So basically, because of this tubular neighborhood theorem, we can connect this gamma of tk plus epsilon to basically u minus x. So u is like my little neighborhood around x, without crossing x, and staying inside of this neighborhood, inside the tubular neighborhood, inside this bn minus 1 times 1, 1. So basically, you go through this, but you never cross the bn minus 1 times 0, which is the part that corresponds to x. Okay? So there we go. So basically, if we look at this path composed with the rest of the path to z, that means that I have a path from z to the neighborhood of x that never crosses the hypersurface x. So basically, when you look at u minus x, that has two connected components. So that means I can connect z either to this part or to this part. Okay, so I can connect. So that means that I can find a path in Rn minus x that connects z to one of these two connected components. So that means that we're done with step 1. So we showed that the complement of x has at most two connected components, because I can do that for a fixed little x. I can connect all points in Rn to this neighborhood without crossing x. Okay, so that's step 1. Okay, any questions about this? No. Okay, so let's go to step 2. So step 2 is if z1 and z2, if z1 and z2 can be connected, in the complement of x, then the winding number of x with respect to z0 is equal to the winding number of x with respect to z1, mod 2. And what does it mean, the winding number of x? Of course, as usual, the winding number of x just means the winding number of the inclusion. Okay, so the winding number of a submanifold, of a hypersurface inside of Rn, is just the winding number of the inclusion. So with respect to a point that's not z1 and z2. To 2 points that are, of course, not on x. Okay? So how do we prove that? Well, if we have a path, so So the proof is actually very simple. So if gamma t is a path, well, let me use z0 and z1 again, because it's nice for the domains to be 0, 1. So if gamma t is a path connecting z0 and z1 in Rn minus x, we can define u t, which is a map from x to Sn that takes little x to x minus gamma of t divided by norm of x. No, that's right. Gamma of t, x minus gamma of t divided by norm of x minus gamma of t. And now, because this path is contained in the complement of x, that means this map ut is well defined for every t. The denominator is never 0. So this is a homotopy between sort of u of z0 and u of z1. So that means that the degree of u z0, which is by definition the winding number of x with respect to z0, is equal to the degree of u z1, which is the winding number of x with respect to z1. So this step 2 is pretty straightforward. Okay, it's exactly what you would think. Okay, step 3 I think is kind of the most interesting one. I mean, step 1 is also pretty important, but let's go to step 3. Step 3 says that basically when you cross the hypersurface, you change the winding number by 1. Okay, so that's really showing that there has to be more than just one connected component. So far we know that there are at most 2 connected components, that if you stay within one of them, or if you stay within a connected component, then you can't change the winding number. So step 3, basically if L is a line segment connecting z0 and z1, and of course z0 and z1 are not in x, and L intersects x transversely, and their intersection is just one point, and the intersection of L with x is just a single point P, then the winding number of x with respect to z0, these are all winding numbers, everything here is mod 2, because I don't have any orientability. Then this winding number is equal to the winding number of x with respect of z1 plus 1, mod 2. Okay? I mean, I don't have to write mod 2 because these things are in z2. So, okay. All right. So I guess this is kind of what, in my opinion, the crucial point. Okay. So how do you prove that? It's actually simple if you draw the right picture. So think of this as being your x, and then you have z0 and z1. And the property that we're requiring is that the line connecting them, there is a line, but anyway, it could be a curve. But I'm asking for a line, and then later we can kind of do stuff with other curves. But I want this line to be transverse to x. Okay? So then I'm claiming that the winding number has to be different. Okay. So how do we prove that? Well, so I'm going to let V be equal to Z1 minus Z0 in Rn. And since L is transverse to X, that implies that UZ0 is transverse to V over norm of V, and UZ1 as well. So this is the argument I've alluded a few times. That, this line being transverse to this, it means that, when you look at the point, when you basically look at this difference divided by this norm, this is going to be a map into a sphere. And then there's going to be, this is going to be a regular point of that. And I guess you should put a parenthesis here. So it's the same thing as saying that this vector here is a regular value for both of these maps. Okay? So this is the implication that I referred earlier as an exercise. Okay. So now it's actually pretty simple because so V over norm of V is a vector that points in this direction. So now what you see is that when you look at the preimages of UZ0 of V over norm of V, this is going to be equal to the preimages of UZ1 of V over norm of V. So if you are a point in X that's in this direction here, and you're sort of beyond Z1 in this line, then you're going to be seen by UZ0 and by UZ1. I mean, if you're an intersection on the other side, then you're not going to be seen because you're just taking the preimage of this vector. So it's not the whole line. It's just the points in the positive direction. So you see all of these guys, but Z0 sees one more. It also sees this point here that UZ1 doesn't see. Okay, so this joint union with the point P. So that's basically it. You have one extra intersection point, or one extra preimage. So that means that the degree mod 2 of UZ0 is equal to the degree mod 2 of UZ1 plus 1. Okay, and this is by definition the winding number of X with respect to Z0, and this is the winding number of X with respect to Z1 plus 1. So that's step 3. You see, it's very simple, but it's very important. This is kind of the crucial step. And finally, I guess the step 4 is just concluding. This is the conclusion. So step 4, conclusion. So now we do the following thing. So we let W be a point that's really big, whose norm is really big. So, for example, X is compact, so it's contained in some ball, and you take some point that's outside of that ball. Actually, sorry, you don't need this. You can just define the following thing. So you let U1 be the set of Z's such that the winding number of X with respect to Z mod 2 is equal to 1. And you define U2 to be the set of points such that the winding number is 0. And then, these two sets, they have to be open. But they're also, closed inside of this guy because of this property because of step 2. So anyway, these two, it's by the previous steps. These two are the by the previous steps. U1 and U2 are the connected components. Are the connected components of Rn minus x. And it's very simple to see that when you add x, that x is a boundary of both of them. So it's kind of simple. It is simple to see that the closure of U1 is just U1 union x, and the closure of U2, which is just U2 equals x, union x, are manifolds with boundary. With boundary x. That's just, take a point in x, and you look at a neighborhood of that, and basically you have a little piece of U1, a little piece of U2, and they're just canonically, just, if you take a little piece of the neighborhood, then you have this, and it has to be, one side has to be U1 and the other side has to be U2. So you have a little a little neighborhood of the boundary. Okay, so one of them has to be U1 and the other has to be U2. You don't know which one it is in principle, but one of them they have to have different winding numbers, and the whole thing has the same. The two connected components have the same winding number. And to finish, the last thing you have to see is that U1, the closure of U1 is compact, and equivalently, and the U2 is unbounded. So how do you show that? Well, we basically show that if you take a very large point, a point with very large norm, then it has to be in U2, and it can't be in U1. So basically, so what you do is the x is compact, so x is contained in some ball of some radius r. So now if z is a point that's not in this ball, so that means the norm of z is bigger than r, then basically you can then tx minus z. So then if x is in the compact set, then tx minus z is bigger than or equal to the norm of z minus t, the norm of x. But if t is between 0 and 1, then because x is contained in this ball, this is greater than 0. So that means that that uz is homotopic to a constant map. A constant map, sort of z over norm of z. Okay? So that means that the degree of uz, which we know is the winding number of x with respect to z, is equal to 0. Okay? So that's it. So that's the end of the proof. Okay. Any questions? Comments? Okay, great. So we did 2 beautiful theorems today, and tomorrow we're going to do some more beautiful theorems, applications of intersection theory. So see you tomorrow.